Welcome to MSP lecture series on advanced transition metal chemistry. In my previous lecture I had initiated discussion on metal-metal multiple bonding, and also I gave you some background to metal-metal multiple bonding by the work carried out by Cotton's group, especially while working with rhenium salts. Let us continue from where I had stopped. Before we try to establish a bonding concept such as molecular orbital theory, to understand the nature of these bonds, let us try to classify the metal-metal bonds we come across among coordination compounds and organometallic compounds. In general, there are three classes of metal-metal bonding we come across in coordination chemistry as well as in organometallic chemistry. They are covalent bond. First one is covalent bond. So, here they are electron precise bonds. bonds counts as one electron from each metal center. So, most common type of metal-metal bonding we use while electron counting, and also to know whether a given complex satisfies 18 electron rule or not, especially when we have more than one metal center in a complex. So, that means this is a covalent bond. And then we have another type of bonding called dative bonding. So, one metal uses a lone pair from the filled d orbital to coordinate to an empty orbital on a second more unsaturated metal. For simple electron count purpose can be considered as covalent bond, but here what happens, one metal is electron rich, other metal is electron poor, and it has vacant orbital. So, that the electrons can be given very similar to what we come across in case of acid base interaction, Lewis acid and Lewis base interaction, that is called dative bond. For example, if I take a metal center having 18 electrons and other metal having 14 electrons, so it can give, and that can also become 16 electron complex if not 18 electron. Now, we have the last one, very rare one, that is called symmetry metal-metal bonding. What does it mean? So, weak metal-metal interactions caused by molecular orbital symmetry interactions of filled empty metal-metal bonding and or anti-bonding orbitals seen in case of D8 metals, but they are less common in nature. Now, let us come back to Re2Cl8 dianion. Here you can just imagine this molecule in this fashion or in this fashion, and here this xy plane is there, and your principal axis is z axis, in which two rhenium atoms are establishing a metal-metal bond, and now we have 4 chlorides here and 4 chlorides are here, and here for all practical purpose let us consider this as z axis here, and then this is xy plane, and accordingly we have to consider the d orbitals for their overlapping to establish various bonds to accommodate these electrons present on metal to arrive at different bonds between two metal centers. So, here we have a quadruple bond, that is 4 bonds between two rhenium atoms, and we have to show convincingly using a MO diagram. Let us say if you consider this is the z axis, if it is the z axis, what happens, we have x square minus y square is there, and then little angle we have xy at 45 in the same plane, and then we have dxz and then dyz is there, and dz square will be in this fashion. So, that means now if two rhenium atoms are in z axis, let us say they can overlap something like this, this is dz square. So, this overlapping you can call it as sigma bond, and now if we talk about pi bond, let us assume this is dxz and this is another dxz, this is another dxz from 2, and if they overlap, this is pi overlapping, this is one xz, and then this one is yz. So, this will degenerate, so that accounts for 2 pi bonds, and then this one is dz square accounts for 1 sigma bond. Now, we have xy is like this now, xy is like this. If the xy is like this, now they do not have any option other than overlapping like this. This kind of overlapping we do not come across in main group chemistry or in organic chemistry when we talk about pi bonds, because this is not pi bond. Pi bonds will be something like this, this is dxz and this is dyz, and then this is dz square, and now if you look into the orientation xy is like this, so they overlap sideways. So, this is XY. So, this is responsible, this is called delta bond. The higher energy of this one is very high and the lowest one is dz square, okay, and the next one will be these two dxz and dyz, and then we have dxy. Now, assume like this, it is there, this is the z axis and one dz square is there, another dz square is there. And now if you ask me why we are using only 4 orbitals such as dz square, dxy, dxz and dyz, why not dx minus y square? If you just look into this ML4 square planar complex formation, and if you recall again valence bond theory, in valence bond theory we are using sp dsp2 hybrid orbitals. If it is dsp2 hybrid orbitals, the d orbital is dx minus y square. That means dx square minus y square is already participated in making metal to ligand bond, as a result that is not available for metal metal bonding. That is the reason we are not considering. So, other orbitals that are left unutilized while making metal to ligand bond are dx square minus y square is used, so dxy is not used, dxz is not used, dyz is not used and also dz square. That is the reason we are using these 4 unutilized bonds to establish bonds between two metal centers. Now, so you bring this Cartesian coordinates, so that can give you precisely the orientation of different orbitals. Once again, you take this one here, another plane, so another plane. So now we put, now this is what we are considering, 2 are in this plane. So you can see now how sigma bond is established between two dz square which are along z axis. So now with this one, let us continue forming other bonds. So one bonding molecular orbital is formed, one anti-bonding is formed here, and now this is sigma bonding and this is sigma star bonding. If 2 electrons are there, 1 electron here, 1 electron here, they come here and one sigma bond will be established. Next we have dxz and dyz, they degenerate here. So they overlap like this and they overlap like this to generate bonding and anti-bonding molecular orbitals having pi symmetry. So 2 are there. So capacity is 4 electrons. Now consider dxy, and this dxy will be forming delta and this will also be delta, but this is sigma bonding and this is delta anti-bonding. This is delta bonding, whereas this one is delta anti-bonding. So this is how you can explain quadruple bonding here. If you have 4 electrons are there, 1, 2, 3, 4. So here 2 electrons are there, here 4 electrons are there, here 2 electrons are there, 8 electrons are there. Here we do not have any electrons. So bond order would be C8 minus 0 by 4. So that is 8 minus 0 by 2. So that is 4 bonds. So that explains the delta bonding or quadruple bond between 2 rhenium atoms. So now to make it clear, again I am showing you. So this is sigma bond, this is one of the pi bonds and this is the second pi bond, and then this is the delta bond with dxy, to sideways overlapping. Okay. And now that leads to this sigma molecular orbital and this one 2 pi bonds in this fashion at orthogonal to each other, and then we have the delta bond. So that means we have a sigma bond, 2 pi bonds and 1 delta bond. They are responsible for making bonding molecular orbitals, and remaining will go in the same sequence, delta, pi and sigma, they will be anti-bonding orbitals. So this is how, using in a very simple way, one can explain the multiple bonding between two metals in coordination chemistry. To even further simplification, I have used these cartoons. You can see this is sigma bond, head on collision, and this is one of the pi bonds. Okay, now this is orthogonal, another pi bond, and now we have delta bond. I hope it is very clear now how to write bonding molecular orbitals and anti-bonding orbitals to show the magnitude of bonding among coordination compounds if there are metal bonds. So now I have shown here what would happen if you have more than 4 electrons. So that means D1 we put 2 electrons here, that results in a single bond, and D2 what happens, we will be having 2 electrons here and 2 electrons. So bond order will be 2, so it will be a double bond. If you have triple bond, we will be having 2 plus 2 plus 2 here, 6 electrons, 3 from each. So we have a triple bond, and if you have 4 electrons from, that means D4 system, we will be having a maximum bond order of 4, that is called quadruple bonding. And then the fifth one will be, if you have one more electron, so that goes here a pair, so that means 2 4 2 2 10. Now the bond order will decrease, so it will become a triple bond. Similarly, if you go with the D6 electrons, then it will become double bond, and D7 up to here completely filled, you have a single bond. If D8 system, both anti-bonding and anti-bonding are completely filled, so bond order is 0. No net bonding results in case of D8 system in this fashion. So this can give an idea about the nature of the bond through simple electron counting here, simple electron counting and placing them here. What you should remember is, you should remember 1 sigma, 2 pi, delta, delta star, pi star, sigma star, that is it. And dz square is responsible for sigma bond, and dxz and dyz are responsible for 2 pi bonds, and dxy is responsible for delta bond, and in a similar fashion. So we can see the corresponding anti-bonding molecular orbitals. Now let us look into some examples here. So 4 electrons, as I mentioned, you can start putting here 2 2, first they are singly occupied, and then you have they are doubly occupied 6, and then yes. Okay, so this explains. Now 8 electrons are there in the bonding, so bond order is 4. Now let us look into this molecule here. First you have to identify tantalum, nothing doing, identify tantalum metal here. Okay, tantalum means where it comes you should know, vanadium, niobium, tantalum, that means it has D3S2. D3S2 means 5 electrons are there. If 5 electrons are there, and you have to identify anionic ligands. So we have 1, 2, 3, 4, 5, 6, 6 are there. It has a symmetric structure, so that means each one would contribute 3 electrons, so that the titanium is in 2 plus state. D3S2 loses 3 electrons, and then we have a D2 system here. If D2 system is there, you can go back to the previous diagram and see whether we have a double bond between 2 tantalum atoms. We have a double bond between 2 tantalum atoms, and then here the tantalum bond is 2.68 angstrom units. Now let us go to another example here. So now we look into this one. Each molybdenum has 2 carbonyl groups and 1 CP group is there. And of course here molybdenum is, let us consider D4S2, 6 electrons are there, and now 1 is negative. So molybdenum should be in +1 state. As a result, what happens, this is a D6 becomes D5. If D5 is there, you should recall the previous diagram I showed you. So D5 will result in how many electrons? It is D8. So if you put here 2 electrons, 4 electrons here, and then 2 electrons here and 2 electrons here. So this is sigma, 2 pi, and then delta, delta star. So 10, 2, 4, 6, 8 minus 2, 8 minus 2, 6 by 2. So there should be a triple bond. Yes, there should be a triple bond. Okay, so triple bond is there. So, okay. So now you go to this one here. So here we have trianionic ligands are there. So molybdenum is the same, molybdenum D4S2, but molybdenum is in +3. 3 plus 3 state means what we have is out of 6, 3 D3 system. So D3 system, how to write? So here 6 electrons are there from one D3 here and another D3 here. So what we have is 1 sigma 2 pi. So it should be 3 triple bond. So triple bond is there. So this is how you should be able to identify the magnitude of metal-metal bond simply by electron counting, and then adding those electrons to already established MO diagram that I have given to you in the order sigma, 2 pi, delta, delta star, 2 pi star and then sigma star again. So, here molybdenum distance is 2.17 Angstrom units and it has a triple bond. This is almost identical with Re2Cl8 dianionic compound. So, D4 system, this is again D4 system, and what is interesting is despite CH3 groups are very bulky, still it prefers eclipsed conformation so that it can establish delta bond. What happens, the other one turns this way, what happens, your XY won't be having in the same fashion, it will be something like this, they have to be something like this, both the XY. If it turns something like this, there is no overlapping. So, in order to have this one facing each other exactly like this for sideways overlapping, they have to be eclipsed. That is the reason despite it overcomes kinetically stable staggered conformation and prefers eclipsed. Of course, in order to minimize what happens, it lifts these 4 orbits little up and this one down so that it can have a quadruple bond. Okay. Okay. So, now this is very similar to what I showed for molybdenum. Again you should anticipate a triple bond between these 2 chromium atoms. Yeah. Here chromium distance is 2.27 Angstrom units. Now, let us look into this example here. In this example again we have this pyridine is there on each one neutral ligand and we have a bisphosphine is there bridging 2 metal centers niobium, vanadium, niobium, tantalum, and we have again a D5 system 1, 2, 3, 4, 5, 6 are there, that means we have to get rid of 3 electrons for each one. So, it is D3S2 is that, let us assume D5, if you remove 3 electrons it becomes D2. So, D2 system, in D2 system you will be having a double bond between these 2. Okay. So, that means in this one it has a double bond between 2 niobium atoms. It is very simple, it is much simpler than doing 18 electron rule, but do not mix up 18 electron rule with this way of electron counting, they are 2 different entities. You should remember, you should not even make an attempt to make it satisfy or obey 18 electron rule, because early metals or metal ions having less than 6 electrons in their d orbital which are available for bonding, you cannot have, even with octahedral geometry you cannot satisfy 18 electron rule. So, 18 electron rule is a different concept, and then looking into the nature of the metal-metal bond in this kind of molecule is a different concept. Please do not try to mix up, even if somebody asks a question they are referring to different concepts, okay, one need not have to worry about that one, but there is no harm in verifying whether a given molecule, the magnitude of the bond, metal-metal bond can be explained using both the methods. We may have some examples, but you cannot generalize for all complexes or coordination compounds both the methods. Now, let us look into another interesting molecule here. We have osmium compound, we have 4 acetates are there, and also we have a osmium chloride bond on each one. So, that means here you should know that acetate is a monoanionic, 1, 2, 3, 4 monoanionic are there and 2 negative are there. So, that means basically 6 anionic ligands are there, each one should go to osmium. So, they pull out 3 electrons from each osmium metal. Osmium is D6S2. So, out of 8 electron, D8 electrons you have to take out 3, 3 means you will be osmium is 3 plus, this is a D5 system, is a D5 system, we will be having a triple bond. Okay. How D5 system will be triple bond? Again 2 pairs here, sigma, pi, 2 pi and delta we have 2 electrons, and then delta star we have 2 electrons. So, 10 electrons are accommodated, and now what we have is a triple bond. So, 8 minus 2, 6 by 2 equals 3. So, you should have a triple bond. So, easy. So, you can see now triple bond order is 3. So, this is how, no matter which metal ion is given, you can also say how many bonds are there, whether the bonding is possible or not, all those things you can analyze simply using this a very general MO diagram. So, now I have another interesting molecule here. I have shown the molecular formula I have given here, and how to write the structure. Yes, you can take the compound here. So, this is how the ligand is described. If you see here, the valency is not satisfied, this should be negative charge, this should be negative charge, and this is phosphonium positive charge. So, that means 2 negative charge and 1 positive charge is there, and then this can also, one can write something like this. So, it should be something like this. So, now this looks almost isoelectronic with acetate, that means we have 4 of them are there. How the 4 of them will be forming bond? Something like this, 1, 2, 3 and 4. So, that means just one I write. So, then another one should be something like this, I can write, another one I can write something like this, other one something like this. Now 4 are there. So, 4 are there, and this is a, let us assume we have 6 electrons are there, 1, 2, 3, 4 anionic are there, 2 each. So, it will be a D4 system. If it is a D4 system, very similar to rhenium case, you can anticipate a quadruple bond between them. Okay, you can see anionic ligand, and then resonance structure when you write, this is how the structure you can write, and you can see yes, this molecule has a quadruple bond. So, 4 anionic ligands and 2 chromium atoms are there, and chromium is in +2 state. Once it is in +2 state, it is a D4 system. Obviously, it shows quadruple bonding. Let me stop here. Another interesting question that comes to your mind is whether we can have more than 4 bonds between 2 metal centers. Yes, we can also have 5 bonds, that is called quintuple bond. So, what are the conditions for a metal complex to have a quintuple bond? That is discussed with a couple of examples in my next class. Until that, okay, enjoy metal multiple bonding concept, reading and understanding it.